Have you ever watched an Olympic weightlifter right before they step up to the bar? Think about it for a second. They don't just casually stroll up, grab the medal, and hope for the best. Absolutely not. They chalk their hands, they take a massive, centering breath, they focus their mind completely on the mechanics of what they're about to do, and then, boom, they apply maximum explosive effort in one highly coordinated, incredibly technical burst. It's all technique, power, and precision happening in a matter of seconds. Well, I want you to hold on to that specific image today because tackling those high-mark, extremely demanding Cambridge IGCSE physics questions requires exactly the same approach. You cannot just casually walk up to a 4-mark explanation question and hope your scattered knowledge lifts the weight. You need explosive power, and you need maximum effort delivered in short, highly structured bursts. Welcome to this explainer. Today we are focusing squarely on syllabus code 0625, and specifically we are taking on one of the most notoriously tricky, trap-filled topics in the entire curriculum, the thermal expansion of solids, liquids, and gases at constant pressure. We're going to look at its applications, its real-world consequences, and most importantly, the underlying explanation in terms of particle motion. Okay, let's dive into this. We are going to treat your exam strategy exactly like a high-performance sport.
Now you might be thinking, thermal expansion? Things get hot and they get bigger? What's the big deal? Well, this isn't just my opinion. This is a direct word-for-word quote from the Cambridge principal examiners themselves. They explicitly state in their reports that thermal expansion is one of the most misunderstood areas in physics. So why is that? Why do so many smart, capable students drop the ball here? It's because this topic demands that you bridge a massive gap. You have to connect the macroscopic world, the big things we can actually see with our own eyes, like giant steel railway tracks buckling in the intense summer heat, or the tiny column of red liquid visibly rising inside a glass thermometer. You have to connect that to the microscopic world, the completely invisible, chaotic behavior of atoms and molecules. Students consistently struggle to connect what they physically observe with what the particles are actually doing behind the scenes. The examiner's playbook tells us that candidates frequently lose marks not because they don't know the basic physics facts, but because their explanations lack the absolute precision and the rigid structure required at this top tier of testing. We are going to fix that right now today.
So here is the million-dollar question for you to ponder. Why exactly do students find evaluating evidence and drawing conclusions so incredibly hard, especially when they are asked to explain thermal expansion in terms of particle motion? Really think about it. You probably already know that basic trivia. You know that gases expand significantly more than solids when heated. That's a given. But when a 4-mark question stares you in the face and asks you to evaluate exactly why this happens at a constant pressure using the kinetic theory of matter, total panic sets in. The difficulty lies entirely in translating a simple memorized fact into a rigorous, unbreakable logical sequence of evidence. You have to talk about kinetic energy. You have to talk about the amplitude of vibration. You have to discuss intermolecular forces and the literal spacing between the particles. It is like building a bridge out of logic. If you miss just one step, one single plank in that logical chain, the examiner literally cannot give you full marks. The bridge collapses. Our goal in this explainer is to build that bridge so strongly that no examiner can tear it down.
To get you out of the middle of the pack and into that elite top tier of grades, here is our game plan, our agenda for today. 1. The challenge. 2. Core principles. 3. The procedural framework. 4. Examiner warnings. And finally, number 5, the critical analysis edge.
Let's kick things off with Section 1, the challenge. We are going to look at some actual past paper scenarios.
I want you to imagine you are sitting right there in the exam hall. The clock is ticking. You open your Cambridge 0625 past paper and you see a classic, heavy-hitting scenario. The question presents a bimetallic strip, or perhaps it's a gas trapped inside a syringe at a constant pressure and it's being heated up. The command word at the start of the sentence says, in bold, explain in terms of particles why the volume of the gas increases. And you look over to the right side of the page and you see it's worth a massive 4 marks. This is it. This is where the heavy lifting actually starts. So how do typical everyday students fail this? Let's take a look at 2 very common, very relatable, yet entirely flawed approaches. First up, we have Alex. Alex is what I call the brain dumper. Alex sees the word heat and just writes down every single thing they've ever learned. Alex writes, heat gives particles energy, they get hot, the particles expand and take up more room because it's a gas. Now on the surface, that sounds kind of like physics, right? Wrong. Alex overloads the page with raw facts, but includes absolutely zero correct structured analysis. And here is the fatal error, the ultimate trap. Particles themselves do not expand. Let me repeat that. Atoms and molecules do not swell up like tiny balloons. It is the space between them that increases. Writing particles expand instantly loses you marks. The examiner's red pen just strikes through it. Then we have Sam. Sam is a bit of a clock watcher. Sam rushes and writes, "The gas expands because its volume increases when heated." Look at what Sam did. Sam has entirely missed the specific command word requirements which ask to explain in terms of particles. Sam literally just restated the question in a different order. Both of these students are leaving huge, easy marks on the table, despite actually having studied the topic.
Moving right along to Section 2, Core Principles. We need to understand the underlying assessment objectives that Cambridge actually uses.
You see, the syllabus targets 3 distinct, very specific cognitive domains. They're testing how your brain works on 3 different levels. First, there's knowledge and understanding. This is the baseline. Do you simply know that solid particles vibrate around fixed positions, while liquid particles slide past each other, and gas particles move rapidly and freely in all directions? That's the foundation. Second is application. Can you take that textbook knowledge and actually apply it to a real-world consequence? For example, can you explain why engineers deliberately leave gaps between sections of long railway tracks, or how shrink-fitting works in industrial manufacturing to bind 2 pieces of metal together? And then third, we have analysis. This is the deepest, most complex level. Can you analyze exactly why gases expand significantly more than liquids do when subjected to the same temperature increase at constant pressure? The entire Cambridge assessment framework overwhelmingly prioritizes this analytical depth over superficial breadth. You need deeply connected conceptual understanding to secure those top grades. Memorizing flashcards is just not going to cut it here.
So, the obvious question is, how do we structure an answer that perfectly hits all 3 of those cognitive domains without rambling? Enter the PEEL framework. This right here is your elite lifting technique. PEEL. It stands for Point, Evidence, Explanation, Link. Top-tier students use this exact framework to structure their answers for maximum explosive impact on the examiner's marking scheme. Let's walk through it using our gas syringe example. First, you make your point. You write, when the gas is heated, thermal energy is transferred to the particles. Simple, clear, direct. Next, you provide your evidence. You write, this increases their kinetic energy and they move faster. You're showing cause and effect. Then comes the crucial explanation phase. You write, because the pressure is constant, the faster-moving particles collide with the container walls more frequently and with far greater force, pushing the boundary outwards. Notice the incredible detail there. Finally, you provide the link back to the question. You write, therefore, the average distance between the particles increases, causing the overall volume of the gas to significantly expand. Boom, that's it. 4 clear, logical, undeniable steps. And what does that get you? 4 marks. No fluff, no brain dumping, just pure, structured physics.
Before we continue, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's keep this momentum going. Section 3, the procedural framework. Let's talk about the technical methodology you need to execute.
What I'm about to show you is the exact step-by-step 5-part methodology used by senior examiners when they write the mark schemes and by top-tier students when they ace the papers. Step 1. Deconstruct the question. You have to interrogate it. What is the command word? Is it just asking you to state a fact, describe a process, or explain a mechanism? Each word demands a totally different response. Step 2. Extract the data. What are the specific conditions? Are we dealing with a solid, a liquid, or a gas? Is the pressure being held constant or is the volume locked? Step 3. Select your analytical framework. In our case for thermal expansion, we are selecting the PEEL framework based on the kinetic theory of matter. Step 4. Execute with clear notation. If the question happens to be a calculation involving changes in volume and temperature, lay out your mathematical working clearly, step by step. Don't hide your math. And finally, Step 5. Present with proper terminology. This is where dreams are made or crushed. Do not ever say particles get bigger. Say the amplitude of vibration increases when you're talking about solids, or say intermolecular forces are overcome when discussing liquids and gases. This kind of systematic, almost robotic processing is your absolute safety net when exam anxiety tries to take over.
Let's actually examine a typical 3-mark flawed answer to see this methodology in live action. Imagine a student writes this regarding a heated solid. The solid block gets heated, so the particles get hot and expand, making the block bigger. If an examiner sees this, it is getting covered in red ink. Why? Because the terminology is entirely unscientific. Particles don't get hot, they gain energy. Particles don't expand, the space between them does. Now let's apply our framework. We deconstruct the prompt, we use the PEEL structure, and we insert laser-precise terminology. Watch this transformation. The revised perfect answer reads, as the solid is heated, the thermal energy increases the kinetic energy of the particles. The particles vibrate with a greater amplitude about their fixed positions. This pushes the neighboring particles further apart, resulting in an overall expansion of the solid's volume. Do you see the profound difference there? We replaced get hot with kinetic energy increases. We replaced the dreaded particles expand with vibrate with greater amplitude and pushed further apart. That level of precision is exactly how you turn a sea of red pen marks into a beautiful row of green check marks.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome to Section 4, Examiner Warnings. This is where we look at the traps that catch even the most prepared students.
We're going to rapid fire through the top 3 mistakes pulled straight from principal examiner reports regarding thermal expansion. Mistake number 1, students simply forget to include the proper format. Listen, if a question explicitly asks for an explanation in terms of particle motion and your entire answer only talks about macroscopic visible changes like the level of a red liquid rising in a glass tube, you score 0. 0 marks. You didn't answer the prompt. Mistake number 2. Students forget to carefully check their presentation and annotation, especially on visual questions or graphs showing expansion curves. Sloppy drawing costs points. And mistake number 3, and honestly this is the most crucial one, answers are just not specific to the context. Writing a generic, the particles move faster, is absolutely not enough if the question is specifically asking you about a bimetallic strip acting as a fire alarm. In that specific context, you must explicitly state that the brass expands more than the iron for the exact same temperature rise, which is the physical reason that causes the strip to bend and complete the circuit. Context is king in Cambridge physics.
Now, the absolutely crucial point I want to make here revolves around what we call the method mark strategy. Let's say you are hit with a brutal, multi-part question calculating the precise expansion of a liquid, or maybe calculating the thermal energy required to cause a state change right before expansion occurs. On one hand, you have a student who panics, punches some numbers into their calculator, and just writes down a final answer that happens to be mathematically incorrect. Result? 0 marks. Nothing. On the other hand, a second student gets the exact same wrong final answer due to a silly calculator typo, but they showed their logical steps. They wrote down the correct physics formula. They visibly extracted the given information from the text. Guess what? The examiner awards them method marks. They might get 2 out of 3 marks for a wrong answer. Never ever leave a calculation or a multi-step physics problem blank, and never just write the final number. Always show your procedural working. It acts as an incredible insurance policy for your final grade.
All right, it is time for an interactive challenge. Wake up, look closely, and take a look at this paragraph explaining why a simple party balloon expands when left out in the hot sun. I want you to visually scan it like an examiner. Here is the text. When the balloon is left in the sun, the air inside gains heat energy. The gas particles absorb this heat and expand, becoming lighter. Because they are moving faster, they hit the rubber walls more often, making the balloon larger. I'll give you a moment. Read it again. Which specific sentence in that paragraph instantly automatically loses marks? Did you spot it? I really hope you did. It's that second sentence. The gas particles absorb this heat and expand. As we have discussed extensively today, the actual physical particles, the atoms or molecules of a gas, do not expand. They don't change size. It is the space between the particles that increases. The particles themselves remain exactly the same microscopic size. Training your brain to catch these incredibly subtle terminology flaws is exactly what separates a standard A student from an elite A-star student. Let's move into our final phase, Section 5, the critical analysis edge. This is about evaluation and high-level insights.
I want you to think of the complete master-level problem-solving blueprint in 3 distinct stages. Stage 1 is deconstruct. You identify every single piece of given information. Ask yourself, are we at constant pressure? Yes. What state of matter is it? Stage 2 is solve. You break the problem into logical, bite-sized steps. For example, if you need to compare expansion, you mentally compare the forces. You recall that gases have essentially negligible intermolecular forces, liquids have weak intermolecular forces, and solids have very strong intermolecular forces. Then comes stage 3, evaluate. This is where the magic happens. This is where you make justified recommendations or draw profound conclusions. For instance, imagine evaluating exactly why a liquid and glass thermometer needs a remarkably narrow capillary tube. You use your critical analysis to evaluate that because liquids only expand a very, very slight amount compared to gases, that narrow tube is physically necessary to force that tiny volumetric expansion into a large, visible, linear movement up the glass. You are questioning the design assumptions and mathematically proving your reasoning to the examiner.
And listen, when you are doing this level of critical analysis, especially if a question specifically asks you to actively compare the thermal expansion of solids, liquids, and gases against each other, you must adhere to strict linguistic conventions. First, identify both similarities and differences. Don't just generically say, gases expand a lot. Say, gases expand significantly more than liquids. Second, deliberately use comparative connectives in your sentences. Words like whereas, in contrast to, or is greater than. Examiners actively scan for these words. Third, support every single comparison with undeniable evidence. Gases expand more because the intermolecular forces between the particles are negligible. Finally, draw definitive, clear conclusions summarizing their relative behaviors. This highly structured, almost legal-style comparison is exactly what the examiner's rubric demands for full maximum credit.
Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.